Let me just send my warm greetings and regards to friends and colleagues throughout the world. I know we represent many different time zones and the differences. So I'm deeply grateful for the engagement of many of you given this particular time work. What we are focusing on is the advent of the fourth industrial revolution has dramatically accelerated the workplace, particularly for the engineering and technical world. The changes brought to higher education and the workforce by the pandemic have also changed both the employees and employees' expectation. I'm just really so pleased that a key leader of our GEDC community of the Global Engineering Deans Council and a leader at many levels globally, Dr. Babak Beheshti, has agreed to facilitate, to give a presentation on this very critical issue at a global level. His experience in higher education spans over 35 years, and he has served as a full-time faculty member, president of the Senate of his university at New York Institute of Technology, and he is dean and professor and so forth. He has been awarded many awards at a global level, working not only with IEEE and the Millennium Medal. And I could go down the list of his very impressive accomplishments. We in the GEDC community are just very pleased to have such thoughtful leader and give this presentation on a fundamentally very strategically important topic today. Dear Dr. Beheshti, dear Babak, please, we look forward to your presentation here. Thank you kindly. And again, welcome to all of you. You'll have about 40 minutes per se. There'll be some questions and answers. You can send them to us, and I'll make some final comments on this. Dear Babak, please continue.
Thank you, and thank you for that very generous introduction. Let me share my screen, and we can now proceed. And before I start, actually, I want to echo what my colleague Aliki mentioned. Happy International Women's Day to everyone. It's fortuitous that this presentation coincides with this very important day. So thank you for the invitation. It is a pleasure to present this talk on the future of work in engineering. I would like to thank GEDC and IFEES who have organized this talk series. The overall flow of my presentation will follow the sequence of topics shown here. So let us begin with the work trends. The global pandemic forced a rapid transition to remote work. While many were skeptical of employee productivity while working remote, the practice permanently changed the workplace for many. According to Gartner, before the pandemic, 30% of US workers worked always or sometimes remotely. After the pandemic, this has changed to 48% of the workforce. A survey by Gartner indicated that 83% of employees report that they are more productive working from home. 77% of employees say that working remotely will help the company lower operating costs. And interestingly, 27% of employers have reported increased company productivity. The shift to remote working makes work more flexible, with 43% of CEOs in one survey granting employees flexible days. The majority of employers have permanently pivoted to hybrid or virtual formats, but few offer targeted training for managers to oversee virtual team members. So according to EMI, as quoted in here in this slide, proper training of managers and employees is a key contributor to effectiveness of remote work. In other words, without proper training, remote work may not be as effective as in-person work. For the first time in history, we have 5 generations simultaneously engaged in the workforce. The younger generation finds remote and flexible work more in line with their lifestyles, and top talents in many situations will select their employers based on their flexible work policies. In addition to the remote work and flexible work schedule, another trend is the shift to independent work. And this shift is from permanent positions or traditional employment. Remote and hybrid work models are part of the new normal. That means greater hiring flexibility for businesses that can now hunt a much wider pool of the right talent from a much wider geographic area. People have been starved of travel for a long time now, according to MOV Group. Freelancing gives people the freedom to work from anywhere in the world, so it is likely that we see more digital nomads in operation. Digital nomadism also encourages freelancers to take on work in different parts of the world. As more people turn to freelance work, governments are likely to move to protect traditional employment. This could lead to more regulations in the gig economy in the years to come. The potential for remote work depends on the mix of activities undertaken in each occupation and on the physical, spatial, and interpersonal context of them. McKinsey has assessed the theoretical extent to which an activity can be done remotely. This depends on whether a worker needs to be physically present on site or do a task, interact with others, or use location-specific machinery or equipment. Many physical or manual activities, as well as those that require those of fixed equipment, cannot be done remotely. These include providing care, operating machinery, using lab equipment, and processing customer transactions in stores. In contrast, activities such as information gathering and processing, communicating with others, teaching and counseling, and coding data can theoretically be done remotely. Extrapolating this to engineering fields, many design, analysis, programming, and testing jobs will easily fit into the flexible work model. Preparing the workforce of 2030 therefore requires instilling a new set of skills from the early education stages, including active learning and incorporating technology into the classroom from the earliest stages, creativity and critical thinking, communication skills, and independent work skills. As you will see, this theme will come back again and again during this presentation. 35 technologists from around the globe came together as part of an ongoing effort to develop the IEEE Computer Society's Technology Predictions Report for 2023. In Q4 of 2022, these technology experts met to come up with 19 trends most critical to engineering today. The report not only produced this list, but also delivered a comprehensive analysis of each technology's predicted success, the potential impact on humanity, predicted maturity, and predicted market adoption, and includes horizons for commercial adoption opportunities for academia, governments, professional organizations, and industry. These trends are noteworthy as we prepare the future generations of the engineering workforce. So you do see the 19 technologies listed in here. I urge you to look up the report. And now let us take a look at the trends in universities and higher education. There is no doubt that the higher education institutions need a digital strategy. Key is getting senior leaders to play the important role of working across campuses to establish a shared understanding and identify problems and opportunities while being intentional about requiring digital solutions. Standing still is not an option anymore. IT units must be able to respond thoughtfully and partner effectively with different areas of the institution to design, implement, and monitor innovative initiatives. A strong digital backbone managed by a CIO that is dedicated to institutional goals will be necessary in digital transformation. The CIO will be the architect of the interconnected systems that will have to be compatible with anything new brought in. University digital transformation goes way beyond lecture recordings, however. And students and professors now find themselves able to participate in classes no matter where they are in the world, thanks to a fully digital, virtual, hybrid, and high flex classroom options. For universities, digital transformation can increase competitiveness, expand both the student and faculty recruitment pools, grow enrollment, and allow for data-driven evaluation and decision-making. In June 2021, the European Union project called Universities of the Future held a final conference to discuss the results for Industry and Education 4.0. The partners produced their blueprint for Universities of the Future, which featured 3 Industry 4.0 challenges. These include a lack of understanding of how to prepare for future work, a lack of a skilled workforce, and a lack of vision for technology. The partners postulated that we need to educate T-shaped individuals who have a deep understanding of domain-specific skills, as well as a breadth of knowledge of systems-oriented and transferable skills, including interpersonal skills, digital skills, the ability to learn, project management, and so on. The partners envision scenarios for 2040 in which higher education institutions have close cooperation with and serve as bridge builders amongst industry, government, and non-government organizations. Let us compare the demand for various engineering disciplines over a decade. According to the American Society for Engineering Education data, the top 3 engineering degrees awarded in 2008 and 2009 in the US were mechanical, civil, and electrical engineering. While the 3 smallest number of degrees awarded were in engineering management, mining, and computer science degrees offered outside of the colleges or schools of engineering. In contrast, in 2021, but more than 10 years later, the top 3 awarded degrees now have civil engineering replaced by computer science degrees offered within colleges or schools of engineering. It is noteworthy that the number of computer science degrees awarded 10 years ago was 5,600, and now the number has grown to 19,900. The 3 lowest awarded engineering degrees remain consistent with 2008-2009 data. Global undergraduate degrees. So from 2000 to 2014, there was a steady increase across several countries in the number of bachelor's degrees or equivalent, termed first university degrees for international statistical comparisons, in engineering awarded as seen in the National Science Board's Science and Engineering Indicators 2018. While in 2014, the United States awarded 119,000 engineering degrees, China leads in awarding first university engineering degrees among selected countries with more than 1 million. The Science and Engineering Indicators shows that in 2014, across several countries, women represented less than half of first university engineering degree holders. For example, in the United States and in the United Kingdom, only about 20% of first university engineering degree holders were women. Australia and India had a higher proportion of women achieving the same feat, 27 and 32% respectively. As you will see, this ties closely to the last section in this presentation. This graph clearly shows the accelerated growth of engineering degrees offered in China as compared to the other select countries. As this slide and the next slide illustrate, according to National Science Foundation's Science and Engineering Indicators, the number of science and engineering degrees awarded has increased at all levels and across many fields. In numbers and as a percentage of total degrees, science and engineering degrees increased at the associate's, bachelor's, master's, and doctoral levels from 2000 to 2019. And in this slide, you do see the percentages of the whole. This chart illustrates the dramatic market demand for technical disciplines as compared to more traditional disciplines such as social sciences, humanities, and agriculture. Again, this information is limited to the US. The source is National Association of Colleges and Employers, NACE, from a 2019 outlook. Similar information is captured by the NACE in this chart as well, confirming the information you saw before. Let us now shift our attention to technology trends. Let me quickly explain the fundamental assumptions behind defining the four industrial revolutions to get us to the point of where we are at and definition of the fourth industrial revolution. So the first industrial revolution began in the 18th century through the use of steam power and mechanization of production. The use of it for industrial purposes was the greatest breakthrough for increasing human productivity. Developments such as steamship or the steam-powered locomotive brought about further massive changes because humans and goods now could move distances, large distances in fewer hours. The second industrial revolution began in the 19th century through the discovery of electricity and the assembly line production. Henry Ford carried over these principles into automotive production and drastically altered it in the process. While before the station assembled an entire automobile or any other product, now the vehicles or other products were produced in partial steps on the conveyor belt, significantly faster and at lower cost. The third industrial revolution began in the 1970s in the 20th century through partial automation using memory programmable controls and computers. Since the production of these technologies, we are now able to automate an entire production process without human assistance. Known examples of these are robots that perform program sequences without human intervention. We are currently in the middle of the fourth industrial revolution. This is characterized by the application of information and communication technologies to industry and also known as Industry 4.0. It builds on the development of the third industrial revolution. Production systems that already have computer technology are expanded by a network connection and a digital twin. These allow communication with other facilities and the output of information about themselves. This is the next step in production automation. The networking of all systems leads to cyber-physical production systems and therefore smart factories in which production is fully automated. Some of the hot innovations of 2022, such as OpenAI's ChatGPT, which I'm sure you have heard about very often, are likely to inspire their own ecosystems full of related tools and the companies that make them. Demand for for tech workers is growing much faster than the supply. Universities have trouble keeping up with the field's rapidly changing developments and high demands for training. To help such tech graduates distinguish themselves, universities should emphasize sought-after essential skills like communications and teamwork. Most job sectors that are predicted to be high growth over the next decade will require high levels of education. One source claims that high-paying jobs requiring a bachelor's degree or above will face only 29% of job change due to automation, least impacted by job automation. Like the field of healthcare, other high-value and professional, scientific, and technical service-oriented industries are predicted to experience low levels of automation, accompanied by relative job growth. Additionally, given the benefits AI poses to complex, high-skilled vocations, it is likely that AI-related jobs could see an increased share in the economy, a trend that would create more stable, well-paying positions for workers. Artificial intelligence, or AI, will change the future of work, but the consequences will differ across regions and industries. As with past advances in automation, AI will lead to increased levels of productivity, specialization in job roles, and an increased importance of human skills like creativity, problem solving, and quantitative skills. Although AI will increase economic growth, these gains will not be evenly distributed. As you see here, the top 3 professions that will be impacted the least from automation job displacement include executive management, healthcare, and engineering-related disciplines. The US Bureau of Labor Statistics lists the top employing occupations for workers with an engineering degree here. These disciplines are in line with the degrees awarded reported by the IUCEE in a previous slide. Let us now look at the workforce needs. As globalization trends make it that much harder to stand out in today's competitive environment, companies must rely even more on innovation to engineer winning products that will stand out, capture market share, and secure future revenue streams. Unfortunately, shortages in engineering talent with the right skills make this a challenge. A majority of companies project their engineering departments will need to grow over the next 5 to 10 years. Complicating this further, many of the engineers in the largest segment of the engineering workforce, those with over 20 years of experience, will approach retirement soon. As they leave the workforce, it will even put more pressure on the acute need for engineers. This is an international concern, with those in Asia and Latin America especially concerned with more pressure on hiring strategies to recruit new engineers. A Strata Gallup employer survey shows that less than half of managers globally feel confident in their company's ability to spot and recruit the best talent for the job. The Organization for Economic Cooperation and Development, OECD, is an international organization that works to build better policies for better lives. PISA is the OECD's program for international student assessment. PISA measures 15-year-olds' ability to use their reading, mathematics, and science knowledge and skills to meet real-life challenges. So this is a leading indicator of the abilities of the future workforce, particularly in STEM and engineering fields. PISA measures 15-year-old students' ability to think critically and apply knowledge. The 2018 results indicated boys outperformed girls in mathematics by an average of 5 points in the US. In Malaysia, the opposite occurred. Girls outperformed boys by 7 points in science. Girls outperformed boys by an average of 2 points. In Turkey and Malaysia, girls scored more than 6 points higher than boys. So again, the preparedness of the future workforce is highly region-specific and country-specific. The National Association of Colleges and Employers survey found that these career readiness competencies have the biggest gaps between employer perception of importance and student proficiency. Nearly all employers indicated that critical thinking and communication are very to extremely important for college graduates to have to enter the workforce. However, only slightly more than half, just 55% for critical thinking and 54% for communication, rated recent graduates either very proficient or extremely proficient. While professionalism competency is not deemed as important, the gap is still noticeable. So if you look at the chart in front of you, you will notice in the middle column is the importance given by the employers. And in the right column, you see the level of proficiency that the employers see in their employers. And obviously the gap between the two is the gap between what the education system produces and what the workforce expects. As seen here, the largest skill gaps are in critical thinking and communication, as well as professionalism. In the Tech Clarity and Siemens study, the top 5 academic programs that top performers, companies that are considered top performers in recruiting and retaining employees, think best prepare students for real-world industry work are team-based projects, projects that include design and analysis, real-world problems, and multidisciplinary projects. These are the strategies that universities must adapt to provide the necessary skill sets to the industry. In the Tech Clarity and Siemens study, top recommended initiatives and strategies that universities must embrace are listed here. Again, so strategies to be adopted by universities and higher education to prepare the workforce for the industry. So let's talk about the concept of T-shaped skills or T-shaped persons. The T-shaped person is a metaphor used in job recruitment to describe the abilities of persons in the workforce. The vertical bar on the letter T represents the depth of related skills and expertise in a single field, whereas the horizontal bar is the ability to collaborate across disciplines with experts in other areas and to apply knowledge in areas of expertise other than one's own. Even the concept of a T-shaped person will become outmoded. A T-shaped person, an idea that emerged in 1991 and was popularized by McKinsey, describes a person's combination of breadth of knowledge with the verticality of technical expertise. A T-shaped person will no longer thrive in a world in which our work lives become longer because we live longer and more turbulent because of advancements in technology. Learners of the future are going to episodically seek out some sort of post-secondary education over and over again throughout their long working lives. There now is a time axis in the right-hand picture that the deep expertise of an individual, the vertical bar in T, must change as the time progresses. This challenges the old static model of an individual's T-shaped person nature. Human skills, again, we've seen it as a theme in this presentation, like leadership, communication, and problem solving are among the most in-demand skills in the labor market. Beyond traditional industrial automation and advanced robots, new generations of more capable autonomous systems are appearing in environments ranging from autonomous vehicles on roads to automated checkouts in grocery stores and so forth. Automation will accelerate the shift in required workforce skills. We have seen over the past 15 years. Demands for advanced technological skills such as programming will grow rapidly. Social, emotional, and higher cognitive skills such as creativity, critical thinking, and complex information processing will also see growing demand. Basic digital skills demand has been increasing, and that trend will continue to accelerate. In a new learn, earn, learn cycle, workers will need to return to learning throughout their work lives. They need to be flexible and agile, be able to shift and grow over the course of their longer work lives. It is also increasingly clear that the skills that cannot be easily automated, such as systems thinking, creativity, emotional intelligence, and communication, will be the ones needed to succeed in the future. For hundreds of years, institutions of higher education have artificially separated subjects from one another. Separation of subjects like genetics, physics, and chemistry as separate fields have been the norm. As a result of this, as a result of this silo approach in higher education, all too often students are unable to make connections between their knowledge and the real world applications that they will face. And finally, let us discuss diversity in engineering workforce, particularly gender diversity in this context. I will set the framework for this section with a quote from the then William A. Wolf, the president of National Academy of Engineering. Engineering is profoundly creative profession. The psychological literature tells us that creativity is not something that just happens. It is the result of making unexpected connections between things we already know. It's based on our experience. Hence, creativity depends on our life experiences. Without diversity, the life experiences we bring onto an engineering problem are limited. As a consequence, we may not find the best engineering solution. We may not find the elegant engineering solution. So with that said, let us take a look at a number of trends in the US and worldwide. In the United States, while the number of engineering degrees awarded has increased significantly over the past 15 years, the percentage of women receiving engineering degrees has remained relatively flat, somewhere around 20%. Consequently, 4 out of 5 engineering graduates are men. The same trend exists for master's degree recipients of engineering degrees in the US. While the trend is in the upward direction, which is a positive thing, only 29% of degree recipients are women. And for PhD degrees awarded in engineering, the trend mimics that of the master's degrees. In the US, women are attracted to certain engineering disciplines more so than others. Environmental, biomedical, and biological engineering degrees top the chart, while aerospace, electrical, and computer engineering are at the bottom of the chart. In 2019, overall, a greater share of male first university graduates than female first university graduates are from the fields of engineering, manufacturing, and construction. Moreover, among the countries presented in OECD's 2019 Education at a Glance report, India had the highest proportion of women, 28%, with the first university degree in science, technology, engineering, and mathematics, STEM, from the total number of women with the same educational level. Countries that had the lowest proportion of women graduating with a first university STEM degree included Chile at 6.9% and Japan at 7.4%. The science and engineering indicators show that in 2014, across several countries, women represented less than half of the first university engineering degree holders. For example, in the United States and the United Kingdom, as we saw previously, only about 20% of first university engineering degree holders were women. Australia and India had a higher proportion of women achieving the same feat at 27% and 32% respectively. As a consequence of trends of degrees awarded and the leaky pipeline extending the work environment, the gender distribution in the US workforce further illustrates this imbalance. So this is the reflection of what happens at the educational system and how it manifests itself now in the workforce. Globally, the gender imbalance in engineering fields is similar, even though countries and regions manifest variations in the imbalance. It is important to cite different cultural norms as a factor in the variations observed globally. And this is a visual depiction of the concept of the leaky pipeline, the idea being that if you consider a particular group within a discipline, for example, women in engineering, as they progress through various stages in their education and career, due to various external factors, their number drop off. And this is typically depicted as a leaky pipeline. So I will end my presentation here with some quotes from the UN report titled "The World's Women 2015." So these quotes are from that report. Education is a core human right. This is from United Nations General Assembly of Human Rights in 1948. Education is essential tool for sustainable development. Education is indispensable for closing the gap between women and men in respect to social and economic opportunities, key to empowerment. So in conclusion, while gender diversity was discussed in this presentation in some detail, diversity of thought, background, socioeconomic background, race and ethnicity, and many more contribute to a sustainable engineering workforce, capable of managing the fast-changing world that the next generation will inherit. Thank you for your attention.
Thank you so much, Professor Beheshti. This is inspiring and a very important contribution you're making to this incredibly critical issue and topic at a global level. And I'm just very, very pleased, and thank you again, that we have quite a number of very thoughtful colleagues and friends representing some different cultures here, as diverse as, of course, we have a strong participation of friends in India, but a good friend and leader in Brazil that I'm just wondering if possibly she could comment, and also a key corporate colleague and leader of our IFEES GEDC community, Dr. Soma Chakrabarti, and a clear leader in Europe. So I'm just looking also at a geography here, Professor Manuel Castro. I wonder if any of you, the three I'm mentioning, could make some comments, even, of course, raise some questions. A final point at this moment here is, I guess my question to many of us, what are some of the digital strategies needed as we move forward the next 5 to 10 years, building on his comments here? So let me just stop right here. Do any of those names, my colleagues, friends I've mentioned, did they hear me? Are they willing to raise some questions, please?
Hans, this is Soma Chakrabarti.
Oh, wonderful. Please go ahead, Soma.
Yeah. Hello, Dean Beheshti. This is Soma Chakrabarti from ANSYS. And thank you so very much for the presentation citing what has happened in 3 different ways and what are needed. But my question, I mean, like Hans asked, what are the digital strategies we need? But at the same time, how the curriculum should change. That's my question, how the curriculum should change in engineering education, so that I'll be very straightforward, so that ANSYS can get the right engineers when they start hiring.
Thank you so much. Thank you for that question. Again, we have to look at really the entire span of education, you know, from elementary school all the way up to the graduation from universities. So as you saw in some of these slides that I presented, the strengthening mathematics, science, communication skills starts at the very early stages in education. It's not something that could be relegated until much, much later at the university level. So the preparation, proper preparation to enter a STEM field starts much earlier. But to your specific questions, what we can do, what strategies can we employ at the engineering education level in universities? You saw some of the guidelines that I mentioned in the presentation. One is removing ourselves from the siloed approach of the majors and disciplines, electrical engineering, mechanical engineering, and looking at them really as a multidisciplinary compendium. as you know, in the industry today, an employer, an engineer is expected to solve a problem. Those problems are often
Yes.
generic and not specific to a particular discipline. But
Right.
also, as the pace of technology is changing so much that we cannot even keep up at the university level, those fundamental essential skills, and notice I don't call them soft skills, essential skills become much more paramount. I use one example to end my answer in here. So everybody has been reading and observing all of the commentaries about ChatGPT, right? So
Yes.
ChatGPT has an amazing capability to write computer programs in multiple languages. I have tested it myself, and it does write optimized code, however smaller units of code,
Yeah.
much better than entry-level engineers can do. So the level of cognitive sort of interaction here becomes much more important at the human level, right? So
Yeah.
humans and engineers are now supposed to be writing blocks of code as opposed to lines of code. So for us at the engineering schools and engineering colleges, we need to focus on these long-term fundamental abilities and skills of the students rather than specific topics in programming 101 or the types of things that have worked for
Yeah.
decades, but quite frankly are becoming far less relative to the
Yeah.
current technology.
Okay. Thank you very much. And I
Thank you.
think Martin has a question.
Please go ahead.
Yeah,
Professor
hello,
Martin.
Martin Hurk speaking from Europe. Thank you for the presentation. I'm working for Engineers Europe, which used to be called FEANI, and which is also awarding the Euring title. And we have an advisory group from industry trying to figure out what are the challenges for engineers in the year 2050. So what would be the competences needed, the credit attributes and the professional competences you achieve in practice, acquire in practice. And also Switzerland, where I'm based, we're talking about the ETH in the university, what will be the kind of teaching in 2040, not quite 2050. And the question is really, if we have so many interpersonal skills which need training, this is not a problem of curriculum, it's a problem of didactics, I think. And you mentioned that project-oriented training might be the answer. Could you perhaps a little bit talk about that? What would be the implications for didactics?
Absolutely. So again, the tradition that has started from the time of Aristotle for the sage on the stage, the professor being on the stage and conveying knowledge to his or her pupils, needs to be turned around very quickly. First of all, the knowledge that we convey has a very short half-life, can be obsolete very quickly. And studies have shown that that mode of education will not be effective in a dynamic, fast-paced world of engineering today. So to your question, a project-based learning allows the students, one, to work in teams, okay, something that is expected of every individual. We don't necessarily in a classroom encourage that. In fact, collaboration during quizzes and exams is frowned upon, obviously. These projects need to be multidisciplinary and real life type of problems. And this is where a partnership between industry and academia comes into the picture. If we have projects, senior design projects and so forth that are sponsored by industry and judged at the end of the day by the industry partners, the students at the engineering schools will have a heads up in preparing themselves for this very fast changing world. And ultimately, I would tie active learning to this concept of project-based learning as well. Again, studies have shown that students retain much more when they do as opposed to when they listen. So, and again, it really challenges the whole paradigm of teaching that the professoriate, including myself, grew up with. Right? We need to change our role from educators to facilitators. There's a wealth of information that is out there freely available to our students. So the skills that we need to instill in them is to be able to decipher information, good information from bad information, and then be able to synthesize based on the information that they have deciphered. And our role as the faculty members will be essentially facilitators and guides in their journey that starts now, and they will go through this cycle of learning multiple times during that life cycle. I will just end with a comment I heard from my colleague recently in a conference I attended, that while our current generation's life expectancy, again, depending on the region in the world, is nowhere above 90 somewhat years of age, our younger generation will be expected to live well into their hundreds. So with a longer work life, it is expected that the technology will change many times over past the time they graduate from engineering. So it's not educating them for what's happening in the next 10 or 20 years, perhaps for something that they need to be prepared for the next 50 years or so after graduation.
This is very, very thoughtful. I'm just wondering, dear Babak, an important colleague from Brazil is congratulations on your presentation. She asked, the data presented is very up to date. The question is the differences between countries. How can we effectively reduce, and how will AI differently impact these countries from your point of view? What are your thoughts, Babak, on this?
Thank you. Very, very complex question. So I will put a plug in here for GEDC. The Global Engineering Deans Council is an entity that transcends politics, government policies, often cultural norms. And this is a forum that we can impact engineering education globally for the sake of science, for the sake of engineering. So one unifying factor, one harmonizing factor that I will bring to the table is involvement and engagement in GEDC and other education-focused organizations globally. And the second part of your question was how does AI impact this rapid change regionally across the world? Again, I would suspect taking away some variations due to geopolitics, of various countries, the same way that the cellular technology, the internet, was a factor in democratizing information flow, AI to some extent will carry the same role. It will have negative impacts, as I mentioned, in terms of job displacement and changing of the nature of the workforce. But again, the ubiquitous, prevalent presence of AI will at some point be beyond the limits and constraints that governments and other governmental agencies can pose onto their people. So I'm positive. Of course, we all have views of a world run by robots, and we are subjects to it. But I think there's a much more positive outlook in there, that the AI as just an automation tool, like many other tools that we experienced, again, in the past 3 industrial revolutions, that could be a normalizing and empowering factor in many regions in the world.
It's interesting. I just got a question that builds on your comment. What changes have been observed in the student knowledge reception? Is it going to be a situation where students are more comfortable learning through bots than through human teachers? What a fascinating question. What are your thoughts on this, Babak?
Thank you. Again, not being part of that generation, I can only observe and conjecture is the best I can do, as opposed to actually a firsthand knowledge. But from what I am observing, we coined the term digital natives a number of years ago. I think it is even becoming more meaningful today. So children that have been born in the past 10 years or so, roughly, are true digital natives, okay, from their earlier, ages, less than 1 year old. They're exposed to technology. They take it for granted. They get wired, their brains get wired in absorbing and acquiring information in a dramatically different way than our generation experienced and grew up. So to that end, the modes in which the next generation of students will absorb information will be completely different from ours. The access to information through the internet and other sources, curated information. Again, I will never be able to overemphasize the importance of critical thinking to separate trash from real information. But we are no longer the holders of information that we bestow the privilege of our knowledge onto our pupils. That knowledge is there. So our role is to guide our pupils, our students, in accessing the information that is available through the means that they're much more comfortable in, that is available to them. Okay, so how they learn is different, and how we teach them to learn would consequently be dramatically different from how we were taught how to learn.
Yeah, very, very, very thoughtful. And another thoughtful question, talking about online learning, what do you advise about stackable micro-credential? Is that already an issue at your university, your institute?
So generally speaking, I think everybody to some extent has been struggling with this concept of stackable micro-credentials. So on one hand, the promises, the pluses of micro-credentials are noteworthy. Either in replacement of a first university degree, which I will argue against, or as a tool for continuing education, lifelong learning, these stackable credentials will allow learners to accumulate and demonstrate their mastery of these upcoming topics and skills to their employers. So as a principle, it's very attractive. What I have been observing, however, is that many, again, because of the mass proliferation of these micro-credentials, these micro-credentials are not recognized or understood by the industry, right? If every university is offering 10, 50, 100, you name a number, micro-credentials, and we have so many thousands of these universities around the world, for a company in a particular industry, if not impossible, it's very difficult to ascertain the validity and the authenticity of the knowledge or relevance of the knowledge acquired through that micro-credential by an individual that is going to be their employee or a prospect employee. So the jury is out there. We have been actually slow in adopting wholeheartedly the micro-credential concept. And I sincerely believe, in light of whatever that we discussed in the past few minutes and some of the topics in my presentation, a well-rounded, whole human being building in the university education is still critically important, more so than ever in the past. Technical topics and skills can be acquired in various modalities, as we've discussed, right? But creating a human being that has a well-rounded understanding of humanities, social sciences, history, and then use that framework to acquire and retain knowledge is something that's still in the firm domain of universities and cannot be sort of exported to a micro-credential world. that was at least my soapbox.
Well, it's fascinating and inspiring, and I want to be sensitive of the time here. Let me just a final comment here by one of our colleagues globally. Develop flexible programs with dual focus, industry work and research. Plan to solve industry problems as part of dissertation project work thesis. Can you make a final comment, dear Babak, on that comment from our colleague in India?
I think that is, a very sound approach, right? So we in academia have always treated research as something that is within our domain. It's advancement of knowledge that has been sort of the domain of universities. But if you look at, again, the trends in the past couple of decades, a lot of, most impactful innovations have come from the industry, right? So for us to really draw the line and separate, industry practice and research is no longer a valid approach. Including both not only helps strengthening our PhD pipelines and scholars of the future, but also makes us more relevant and our products, which are our graduates, more relevant to their consumers, which are the the industry partners.
Thank you so much for your very thoughtful presentation, and again, respectful of time. And we could spend easily another hour with you. We will certainly share the recording and your presentation with our global community per se. I do want to take a minute simply representing our IFEES and GEDC global community. You have several of our members, but there are some potentially new members. I want you to be aware that we're working very diligently to come together globally again. We have an annual conference in Monterrey Tech. I work very closely with the president and the leadership of Monterrey Tech in Mexico in October. Let me know if you're interested, have questions about that. Very, very important, this global event. Of course, Babak Beheshti, as a key leader of the GDC and others that are here, will be with us also. Secondly, the first time we're meeting regionally, I'm very pleased to work with a rector president of a university in Albania, in Tirana, where IFEES GDC is coming together in a couple of weeks. That different part of the world, we hope to engage leaders, also students, of course, professors, deans, and so forth, and that I'm very, very happy to engage in that with some very thoughtful individuals. We are continuing our well-known global issue, in particular today as International Women's Day, our continued series on rising to the top, working on Southeast Asia and the MENA Arab world per se. We're a little bit delayed in terms of the publications. That's moving forward very much. Since we are a global organization, we work in 6 continents, and I'm in current discussions finalizing for us next year in 24 to have our global conference in Sydney, Australia. So I'm planting some seeds here for you to be aware. I'm very excited to go there, and then combine bringing also New Zealand into our global community. Wonderful opportunity and challenge. And finally, certainly not last, certainly important, our GDC Industry Forum, we're working with China. We'll be meeting at Shenzhen in early January of next year. We're diligently planning in that, and also for a long time bringing together Asian deans in Hong Kong, an organization we help form. And again, people are little by little coming back together at a global level per se. So with that, dear Professor Beheshti, Babak, thank you for your thoughtful, and to see many names here in joining us today makes me really, really happy. And let us stay in touch, stay healthy, be well, and celebrate the special day of International Women's Day. Peace be with all of you. Thank you.
Thank you. Pleasure having me.